Hello, my name is Daniel Fejo, and this is my final lab presentation, Lab 5, Pick Your Own Adventure. For this lab, I used the roll of toilet paper to compare two different motions under gravity. One roll that's simply dropped and another that unrolls as it falls. The main question is, from what heights should I release each roll so that they hit the ground at the same time? To answer that, I will use ideas from rotational dynamics, build a mathematical model, compare it to the experiment, and then look at how changing the object's shape would affect the result. I'll briefly cover six things. First, what the lab is about and what I was trying to measure. Second, the important physics concepts, inertia, torque, and rotational motion. Third, how I solved the problem by hand to predict the height ratio. Fourth, how what I did in the experiment with tracker. Then I'll compare models and data and finish with a quick what if and the main takeaway. The core setup is simple but interesting. One toilet paper roll is just dropped straight down like a point mass. The other is allowed to unroll as it falls, so it both translates and rotates. The goal is to find the ratio of heights, h over h, so that these two very different motions take the same amount of time. This forces us to treat the roll as a real extended object, not just as a falling at g. To handle the unrolling roll, we need moments of inertia. A toilet paper roll is basically a hollow cylinder, with most of its mass in the paper at longer radius, not at the center. Because of that, it resists change in rotation. That resistance is its moment of inertia. Using the correct inertia formula and sometimes a parallel axis theorem lets us describe how easily it spins, which directly affects its acceleration when it falls and unrolls. The next key idea is torque. Torque is the rotational version of force, and for the unrolling roll, it comes from the tension in the sheets of paper pulling at the outer radius. We use T equals inertia times A and T equals Fr to connect the gravitational force to the angular acceleration. Once we have the angular acceleration, we get the linear acceleration at the rim from A equals AR. That value of A is what goes into our time of fall equation for the unrolling roll. Now for the times. For the roll that is simply dropping from height h, the time is just free fall. T drop equals the square root of 2h over g. For the unrolling roll, starting from the height h with linear acceleration a, the time is t to unroll equals the square root of 2 small h over a. We define a height ratio h equals kh, and our goal is to find k so that these two times match. Using the hollow cylinder momentum of inertia in the torque equations, we solve for the angular acceleration and then for the linear acceleration. We then set the two times equal. Square root of 2h equals g over square root of 2h over a. Substituting h equals kh and simplifying, we get h over h equals k equals r squared plus 3r squared over 2r squared. Using typical toilet paper dimension, that gives us k equals 1.94, so the dropped roll should start from about 1.94 times higher than the unrolling roll. To test this prediction, I recorded video and analyzed them in Tracker. I set one roll to be dropped from a known height and another to unroll from a lower height, chosen to be near that 1.95 ratio within the limits of my setup. In Tracker, I marked the position of each roll frame by frame, which produced position time and velocity time data. For this, I could measure fall times, see the different accelerations, and visually compare the motions to what the model predicts. When I compared the theory to the tracker data, the overall pattern matched expectations. The unrolling roll clearly accelerated more slowly than the drop roll, consistent with some energy going into rotation. The graphs weren't perfectly smooth, mainly because selecting the center of mass by hand each frame introduced jitter. Despite the noise, the measured fall times and general trends were close to the theoretical prediction, supporting the rotational model and the height ratio. One subtle issue is that the rolling roll is actually losing mass as the paper comes off. In the model, I treated the mass as constant, which is an approximation. For a typical roll, and relatively short drop distances here, the fraction of mass lost is small. At the same time, as mass is lost, the moment of inertia decreases, partly compensating for the change in weight. So for this experiment, ignoring the changing mass is reasonable, and the decent agreement with data suggests that this simplification doesn't dominate the result. Finally, a quick what if to highlight the main ideas. If we repeated the experiment with different shape, like a hollow ball instead of a hollow cylinder, the moment of inertia would change. Repeating the same torque and acceleration analysis would lead to a different value of k. Thank you very much.